Yes, hi everyone. I hope you're all doing well. And so in this video, I'm going to be covering Chapter 12 chi-square tests. Notably, I'll be looking at the goodness of fit tests in section 12.1. So the idea here is that we want to test out whether a population follows a claimed distribution by using sample data to make this assessment, right? In order to come up with a conclusion over here, we're going to be using the chi-square distribution. Now, the chi-square distribution over here, I'll just show you quickly what it looks like. Chi-square distribution looks like this. It's in fact a right-skewed distribution. And well, the testing we'll be doing over here will always be one-tailed and on the right side. Okay, so that's how we'll be doing our testing. And so the idea is that to conduct a chi-square test over here, we must find a way to categorize our claimed distribution into k categories and get hypothetical counts in those k categories, which we will compare to the actual observed frequency counts for the same categories. Okay, so uh, the idea of categories here goes into a multinomial experiment. Okay, so let's just look at what a multinomial experiment is all about. So a multinomial experiment is about, having k categories in your data, and each category has its own respective probability. So it's much like the binomial experiment, which we saw in chapter 5, where here we were using two categories. Uh, so category 1 was a success, category 2 was failure. Category 1 had a probability P, and category 2 or the failure category had a probability of 1 minus P or Q. And so the two categories had complementary probabilities, giving a sum of 1 when we add them together. In a multinomial experiment, it's the same idea. But now we've got k categories. And so when we add up all these k categories, we must get a sum of 1. Okay. Um, Now, if we are going to look at our data and segregate it into k categories, well, naturally, we will get k different frequency counts. This is, of course, I'm talking about our observed data. So our observed data will have k frequency counts. Okay, and our um, hypothetical distribution will be broken down into k probabilities. So one probability will be assigned to each category, assuming that the hypothetical distribution we are testing is valid. Okay. Um, So here we are. F of I here represents the observed frequency count for each category that we've got. And E of I represents the expected or hypothetical frequency count that we should be getting if indeed the hypothetical distribution that is being claimed in the null hypothesis is true. Okay. So the expected frequency count is as a result of doing a little multiplication here. E of I is equal to n times P of I. What this means is that here I am multiplying my sample size n by the hypothetical probability that I should be getting for category I if my population follows a given distribution. So this P of I here is not arbitrarily chosen. It is rather coming from a specific hypothetical distribution. Okay, or a historical observation that is assumed to stand for this population. Okay, uh, so in a goodness of fit test, we are comparing observed frequency counts to expected frequency counts. Uh, that is how we measure over here. Okay, so here we have the layout of what a goodness of fit test should be like. So in the null hypothesis here, we have a statement that says our population follows a given distribution. Okay. In this first simple example here, we are we are saying that our population follows a distribution, and if that is the case, then it would have the following multinomial probabilities. So these are the different probabilities assigned to each category. Here we've got K categories. The alternative hypothesis over here must say something along the lines that, there is at least one probability stated in the null hypothesis that is different, or, something like the null hypothesis is not observed, or let me see, the population follows a different distribution than that stated in the null hypothesis, something like that, right? So there's no specific one way to write the alternative hypothesis. The idea is that it must contradict whatever is said in the null hypothesis. Then, of course, in order to test out whether the null hypothesis is true or not, we will have to conduct a test, right? So to do the test, we need to have a test statistic. The test statistic here will be computed in the following way. So in this case here, we will be using, this is in fact a chi-square test statistic, which is basically comparing observed frequencies for category I minus expected frequencies for category I, and this difference is squared and then divided by expected frequency for category I. So if I have here, in fact, 4 categories, hence 4 hypothetical probabilities, then I should have here 4 times this expression. This expression should be repeated 4 times and should be added together in order to give me here my chi-square test statistic value. Okay, now of course, in order for this test statistic to have any meaning, I need to conduct my hypothesis testing at a level of significance, which would go right here. So here I'd have my alpha um, statement written right here, where it would be specified to be equal to a value, say, of 0.05, 0.10, um, that sort of thing. So here I would have my alpha specification. And then here in this part, I would have the decision rule. Now, depending if you're using a critical value rule approach, then this would have to be the condition here needed in order to reject the null hypothesis. That is, the test statistic chi-square would have to be greater than the critical chi-square for a level of significance of alpha. Okay. If I'm using the p-value rule, then I would have here this condition would have to be met, and that is that the p-value for my test statistic chi-square right here must be less than alpha level of significance, and then I would be able to reject the null hypothesis. Now let me discuss a little bit more about how the critical value is found and how the p-value must be determined over here. So the critical value over here is found based on my level of significance, but also based on my degrees of freedom. So degrees of freedom here, I know that on your slide it says p minus 1, but it should really be k minus 1. K being the number of categories that are identified in the null hypothesis. So here I'd have here 4 minus 1 degrees of freedom. If I were to use 4 categories, I'd have 4 minus 1 degrees of freedom. That would give me 3. So that would be associated with the chi-square, critical chi-square right here. For the p-value, well, that is based on this little information that I've added here to the slide, and that is that the p-value is determined based on finding the probability of finding a chi-square that is greater than the test statistic chi-square that I am getting over here for a given degrees of freedom k minus 1, so that would be 4 minus 1 equals 3. And of course, always on the assumption that the null hypothesis is true. Okay, so here we are. These two plots here are showing you the different decision rules that what it would look like if you were to use, say, the critical value rule. If you were to use the critical value rule, then in order to reject the null hypothesis, you'd need to over here have a test statistic that lies inside the rejection region, inside this blue region right here. Okay, if you were to use the p-value rule, then your p-value would be this area, this tail area in red, and it would have to be somewhere inside the rejection region. It would have so your rejection region would have to be somewhere out here. It would have to be to the left of this test statistic chi-square, right? In order for you to reject the null hypothesis. Okay, so here we have an example where we're looking at, market shares. So these are the claimed market shares. This would go in the null hypothesis. We're saying that we have a population that follows the following distribution. Brand 1 equals 20%. In other words, P1 equals 0.20. Brand 2 equals 35%. In other words, P2 equals 0.35, etc., etc. So we'd have P1 up to P4 in our null hypothesis with the following numbers. And this will be tested against a sample that we are observing over here with the following frequency counts. This sample is of size 400. So I get this information by adding up my frequency counts across all 4 brands. So here you should get a sum of 400. And the idea is that I will be comparing my observed frequency count to the expected frequency count coming from this hypothetical distribution, multinomial distribution right here. So here we are. This is how we would write the null and alternative hypothesis right here. The test statistic chi-square follows the formula right here. Notice here that we are adding across 4 different categories. So I ranges between 1 and 4 because I've got 4 different categories right here. And so this is what it would look like if I actually plug in the numbers. The 102 minus 80. So 80 here is coming from the formula for EI. So let's go look at that formula once again. Here we are. Formula for EI is this right here. So for E1, I would get here 400, that is my sample size, times P1. P1 here, I think we said was 0.20, right? So 400 times 0.20 gives me 80. Here we are. And so for E2, I would do the same thing. I would determine E2 to be equal to 400 times 0.35, and that would be equal to 140. And so I would be able to get my chi-square value for category 2. I would get another chi-square value for category 3 and another one for category 4. And then I would add them all up to give me my test statistic here of chi-square, 8.7786. So here in Excel, I just want to show you how this is actually done. So on the one side, you've got your observed frequencies. Notice that this total here gives me my sample size of 400. Here I've got my hypothetical market shares. These are the p-values that are stated in my null hypothesis, the probabilities, right? And from these probabilities, if I apply the formula E of I equals NPI, I get here for each category the respective expected values. So this 80 right here is as a result of multiplying 0.20 times the sample size of 400. Okay, I repeat this exercise across all 4 categories. Then from there, I can find my chi-square value for each category. That is by applying here this formula 4 times. And so here I am, I get my 4 different critical chi-square values, and here I get my total. That is my test statistic. Now I can draw a conclusion here by applying the critical value rule. And so I would need to determine what is my critical chi-square. The critical chi-square will be determined based on my level of significance alpha, which here will be 0.05, and on my degrees of freedom. So let's just quickly look at the chi-square distribution right here. So here I see that I've got, let me just enlarge this here. I see that I've got over here my chi-square table. Notice here how there is, a chi-square distribution for different degrees of freedom. In my case here, I am interested in 3 degrees of freedom right here, right? So I'm looking at row 3. If I'm going to conduct my test at a level of significance of 0.05, then I am interested in, this, I'm interested in this column right here. Right. Okay. So this gives me here my critical value of 7.81473. Here we are. So this is where this value is coming from. I now compare my test statistic to my critical value here, my critical chi-square, and I see that indeed my test statistic is greater than my critical chi-square value. Hence, I reject the null hypothesis, right? This is going along the rules over here that we saw before, right? This is it over here. If I were to use the p-value approach, now the p-value approach here, so this is my actual p-value for my test statistic of this much. How do I get this p-value? Well, this p-value, if you notice here, is as a result of applying a formula built in Excel. So let's just investigate a little bit more what this formula is about. Okay, so here you go in your Formulas tab, click on More Functions and find Statistical Functions over here. And so here I've got a whole slew of statistical functions that I can apply, or formulas, I should say. So the one I'm interested in is the chi-square distribution right tail area. This will give me a right tail area right here. And so here I see that I need to input 2 arguments. The first one is the test statistic value. That would be X. And so here I would go and input here my my actual test statistic when I add up all the chi-square values over here. The degrees of freedom here, that's my second argument, would be k minus 1. So k minus 1 over here, so that would be 4 minus 1 is 3. I would input 3 right here, right? And that would give me here my p-value. So that is how I get it right here. And the idea in a decision rule here is to compare my p-value to see if it is less than my level of significance of 0.05. Here it is, and so I conclude that I reject the null hypothesis. Notice how the two conclusions are the same, even though I used different approaches, and that should always be the case when doing hypothesis testing for the same uh, sample data, right? Okay. Okay, so let's continue on over here. Okay. So we see that the chi-square test can be applied to not only uh, predefined multinomial distributions as we have over here. We can also apply the chi-square test to other distributions that are not necessarily multinomial, such as the normal distribution. So in the normal distribution, there's a little bit more work that is involved, and that is that here we have to actually create categories from a normal distribution. Okay, how do we create these categories? Well, we can go by, say, the empirical rule where we've got here intervals. So we've got uh, intervals of one standard deviation above or below the mean. We've got another set of intervals that are two standard deviations above and below the mean, and beyond, right? So that is a good guideline to use in order to create categories for um, a goodness of fit test. Okay, so here, if I'm going to test whether my population follows a normal distribution or not, what I will need to do is create categories that will be stated in my null hypothesis. Let's go take a look at that. I have here an example in um, in the Word document that you'll find in your Done in Class folder. So here we are. Here are the ideas that we are given a sample of 65 observations, and we'd like to know if these 65 observations support the idea that the population of payment times is indeed normally distributed. So the idea is that, I will use my sample data to come up with some sample statistics. So here I have my sample mean. This is coming from these 65 observations, and my sample standard deviation also coming from my 65 observations right here. And so I'm able to compute these values. Let me just check something over here. Yeah, so this is my sample data. So using this data, I can actually get these sample statistics right here. And so I'm going to create these 6 intervals. In fact, here I am asked to use these intervals, and these will serve as categories. So I will have 6 categories that will appear in my my null hypothesis. Okay, so over here, beside this statement, I would have probabilities for 6 categories. And these probabilities would have to be assuming that the the normal distribution is valid. Okay, let's go back over here. So here we are. Um, so what are these actual hypothetical probabilities? Let's take a look over here. Well, first of all, if I am to follow, let me just go find over here. If I am to follow these categories, I need to over here find the actual limits for each interval. Now notice here that these intervals are non-overlapping. In other words, the data points that I have below here, these 65 data points, well, I should not have a data point that lies in, say, this interval and that one, right? A data point can only lie in one of these 6 intervals at a time. And also, these intervals are mutually exclusive, so non-overlapping and mutually exclusive. Okay, so if I apply these formulas right here, I should get my interval limits. Here we are. So if I use X bar and S, I get here for my first interval or my first category, I get here all X values in my sample of 65 that lie below 10.1853. So if my sample was indeed normally distributed here, then I would have here some points that lie below 10.1853. And so I would need to figure out how many actual observations do I have that are less than 10.1853. If I go back to my data, well, I need to find that actual data point that is less than 10.1863. Not obvious. Oh, here we are. Here I've got a data point of 10, right? So that I think is the only observation I have that is actually in that interval of less than this X bar minus 2S or 10.1853. Let's go back over here. So that is for the first interval. For the second interval here, I need to count how many points lie between 10.1853 and here X bar minus S, which gives me 14.1465. So if I go back to my sample data of 65 observations, I should in fact find here 9 such values. Okay, so you repeat this across all 6 categories. And so by doing this 6 times, right, I will now have segregated my 65 observations into 6 categories with 6 different frequency counts. Okay, so that is a first step into, segregating your data into K categories. The next step here is you want to now find what are the corresponding hypothetical probabilities that you should be getting for these 6 defined categories. Okay. So in the first category over here, um, anything that is less than the sample mean minus 2 standard deviations, or in other words, anything that lies 2 standard deviations below the mean. That's essentially what this interval represents. Hence, um, the probability of z being less than minus 2. Okay, I need to figure out what is that probability. So here you see how we go from this statement right here for sample data to a hypothetical statement if the null hypothesis was true. This statement would be converted to this over here if the null hypothesis was indeed true, and that is that the population follows a normal distribution. If that is the case, then basically here what I'm looking at is what is the probability that my of having a z-score for a given observation that is less than -2. That is the same thing as saying what is the probability of having an observation that is 2 standard deviations below the mean. And that is coming from over here, the breakdown where we say that we wish to have the first category being all data points that are 2 standard deviations below the mean. So the hypothetical probability for this would be obtained by looking at your standard normal table, and you would look for what is the probability of having a z value of -2 or less, and this would give me a probability of 0.0228. So basically, it would be this area right here. In the second interval, or in the second category if you want, I need to find that P2. What is the probability of getting an observation in category P2? Yes, of getting an observation in the second category. So um, this would be resolved by determining what is the probability that I have a z value that lies between -2 and -1, right? Again, this is coming from, you know, the definition of the second interval being that we have here the second interval lies between x bar minus 2s up to x bar minus s. In other words, we are looking at this interval right here, the second interval. There is a probability, a hypothetical probability that is associated with this interval. So it is an area. This area here, when I go to my standard normal table, I will need to look for the area that is contained between z equals -2 and -1. This area here is 0.1359. So hypothetically speaking, if my population does indeed follow a normal distribution, then the likelihood of finding an observation that lies between, in this case, um, 2 standard deviations below the mean and 1 standard deviation below the mean should be 0.1359. That's what it means. I repeat this again for the third category. And so now I must find a probability for the third category. I do the same thing. I apply the same logic. Now I'm looking at this interval. What is the probability of finding an observation that lies between 1 standard deviation below the mean and 0 standard deviations below the mean? Using the standard normal table, I am able to solve for this with this statement right here. And this gives me a probability of 0.3413. I continue for the remaining 3 intervals. This time they are on the right of the mean. Okay. And so I get here my 6 probabilities for my 6 categories that will be used in my null hypothesis statement to represent the normal distribution. Okay, now let's just go check what the question is asking over here in that question here. So we have, assuming that the population of all payment times is normally distributed, find the probability that a randomly selected payment time will be contained in each of the intervals found in part A. Then it says use these probabilities to compute the expected frequency under the normality assumption for each interval. So here, what they are asking us to do in this latter part here is to apply the expected frequency count formula. What is the expected frequency count formula? Um, so that is over here. This formula right here. EI equals N times PI. Here we are. That is the expected frequency count for category I. So if we go back to our problem over here, well, I know here that I've got n sample size equals 65. I've got my probabilities, my hypothetical probabilities, which I found over here. I've got 6 of them. And so now all I need to do is find my expected frequency count for each of the 6 categories. Here we are. E1 is equal to 65, that's my sample size, times probability for category 1. Here we are. So I get this value right here. I continue with category 2. Expected value for category 2 is 65 times probability of an observation being in category 2, which I get from this right here. And so I get my expected value. Now notice here these expected values have decimal points, and that is quite fine. You leave it as is, because here these are, hypothetical expected values. They are not real expected values. They are hypothetical values. Okay. So I have now found my expected values. Now let's go check at the questions. And so here in question C, verify that the average of the expected frequencies is at least 5 and that the smallest expected frequency is at least 1. What does this tell us? Okay. So under normal circumstances, in order to apply the chi-square test, what needs to happen is that all expected values for each category must be at least 5. I'm just scrolling up because I want to show you here the conditions here. In order to apply a chi-square test for goodness of fit, we need to make sure that we are observing this condition, that the E of i's must be at least of value 5 for all i's. When that is not met, when this condition is violated, then we can apply some remedial measures. We can either choose to go with this approach, which states that we need to combine consecutive intervals, adjacent intervals, in such a way that the new merged intervals will have expected values greater than or equal to 5. So that is one way of fixing the problem. Of course, once again, you must do this for adjacent intervals. So I would be able to say combine intervals 1, 2, and 3 together, but I would not be able to say merge interval or category 1 with category 5 and 6. That would not work. Okay. That is one way of fixing the problem when I have one EI that is not greater than or equal to 5. Another way is to apply what we call the relaxed conditions. The relaxed conditions here is when one, you've got the average of all your expected values across all categories is of at least 5. Okay. Two, you've got more than 4 categories. And 3, the smallest expected value here must have a value of at least 1. So I'm going to use this set of conditions here, the relaxed conditions, in order to make sure that my chi-square test will give me meaningful results. So let's go look at the EIs that we have over here. So I see that my my EIs are right here. I've got 6 of them. Let's check if the relaxed conditions um, are okay on these 6 EIs. So number 1, do I have more than 4 categories? Yes, I do. I have here 6 categories, so that's fine. Number 2, is the average of all the EIs greater than or equal to 5? In this case, I see that I'm getting a value of 10.833. Yes, it is greater than 5, so that is fine. And 3 um, is my smallest EI at least of a value of 1. And so, yes, I see here that my smallest EI is 1.482, greater than 1, so that is good. Hence, I can use the chi-square distribution. I can use the chi-square test. Okay. So now that I've checked for this, I can now go ahead, write out my null and alternative hypotheses. I'm going to use here a level of significance of 0.05. And so now I can do my frequency count for my observed data. So I will have 6 frequency counts, 1 for each category. In the first one here, I've got f of 1 equals 1, which means basically I've got only one observation in my sample of 65 that is less than 10.1843, I believe. Yes. Then in category 2, I've got 9 observations that are in the specified category here, the specified interval, etc., etc. At the end of um, counting across all categories, I must make sure that I get uh, my sample size count when I add up all the frequencies. And so from here, I can apply the chi-square test statistic formula. And this is the actual test statistic value that I get, 5.4997. Here we are. Then if I apply the critical value rule, then I see here that I will reject the null hypothesis if and only if my test statistic chi-square is greater than my critical chi-square. Remember, critical chi-square is determined by your level of significance alpha and as well by your degrees of freedom. So notice here that degrees of freedom is a little bit different than in the previous example. So here, the degrees of freedom will be equal to number of categories that are used in my null hypothesis, minus 1, but minus m as well. M here is representing the number of parameters that were estimated in order to obtain my intervals, right? So if you remember here, we had sample um, statistics for x for the mean value. We used x bar. X bar came from our sample. So that was one of the parameter estimates. The other parameter estimate that we used was standard deviation. So here we used S, uh, which is a point estimate for population standard deviation. Hence, we had to estimate 2 parameters over here. These 2 parameters were needed in order to, come up with these different categories, right? And in order to come up with hypothetical probabilities for each category. Okay, so degrees of freedom here changes. It is not just k minus 1, but you must also subtract number of estimated parameters. So we come up with 6 minus 1 minus 2 for the two estimated parameters x bar and s, and that gives me 3 degrees of freedom. And so here I get a critical value of this much over here. When I compare the two chi-square values over here, I see that the test statistic is not greater than the critical value, hence I do not reject my null hypothesis. And so that is all for goodness of fit test. I'm going to continue in the next video on using the chi-square test to test for independence of random variables. Okay, thank you.